Welcome everyone. Welcome to this tactical session on HBase optimization. I am Devesh, and today we are going to focus on getting maximum performance from your HBase on your existing infrastructure, not adding more hardware. Here's the reality: most organizations are sitting on 30 to 50% untapped performance in their current HBase cluster. Before we, Okay, before we begin, let me ask how many of you might have experienced the situation where your first instance was to scale out rather than optimize what you have? Okay, correct. That's exactly what we are addressing today. By the end of this hour, you will have an actionable strategy that you can implement immediately to supercharge your HBase performance using what you already own. Okay. So let me go with the agenda. We have exactly 60 minutes and I have structured this to maximize the learning and minimize the theory. Each section builds up on the previous one, and starting with the storage optimization through compaction, moving the data distribution via region management and the memory management, and finishing with the real world proof points. Okay, next slide. Uh, so who is this session for? This session is designed for the practitioner people who actually gets their hands dirty with HBase. Whether you are one getting paged at 2 a.m. And when performance tanks on your designated next generation of the data platform. If I'm not going to waste time on theoretically concept you will never use. Everything we cover today can be implemented this week. If you are completely new to HBase, you might want to grab some of the basics first, but don't worry, I'll explain the key concept as we go on. Okay, uh, let me let me start with the problem statement. Okay, so let's paint a picture that might sound familiar. Your region servers are constantly hitting CPU and memory limits. You need your read latencies are climbing up the roof, and they are climbing to milliseconds to seconds. Your bosses are asking why we need to double our infrastructure budget. Sound familiar, right? The traditional response is to throw more nodes at the problem. But here's what most people don't realize: scaling out often just distribute inefficiency across more machines. It's like hiring more worker to dig a hole when you really need a better shovel. Okay. Today's session is about sharpening those shovels, and we are going to address the root cause, not symptoms. And the best part, these optimization are often deliver results within hours, not weeks. Okay. uh, Smarter compaction strategies. Okay. When we talk about smarter compaction strategies, let's start with compaction because it's often the biggest performance lever that you're not pulling. Think of compaction as organized housekeeping for your data, but housekeeping that directly impacts the performance. Here's the key insight. HBase doesn't just store your data once. Over time, you end up with multiple small files for the same data range. When you read data, HBase has to check multiple files. This is called read amplification and it kills the performance. Okay. Compaction merges these files and remove the deleted data. But here's the critical part. Default settings are designed for the generic workload. Your workload isn't generic. That's our optimization opportunity. Okay. The analogy I like is messy disk. You can still find what you need, but it takes longer time. Okay. Compaction is like regularly organizing your disk, but you need to organize it in a way that matches how you work. Okay. Major versus minor compaction. Understanding the distinction is crucial because they have a very different performance impact. Minor compaction are like daily tidying up frequent, lightweight, minimal disruption. Major compactions are like spring cleaning through but potentially disruptive. The default major compaction schedules runs every 7 days regardless of your data pattern. For high traffic production system, major compaction during the business hours can cause noticeable performance degradation. But skipping major compaction entirely lets delete data accumulate, waste storage, and hurting the read performance. So the sweet spot is scheduling the major compaction during the maintenance window or low traffic period. Okay, we will show you exactly how to do this. Here is a real world example. I work with a financial services company that was seeing 5-second query spike every Tuesday morning. Guess when their major compaction were running Tuesday at 7 a.m. Right when their traders were trying to access the market data, right? Sorry. Key compaction configuration. Okay. These parameters control how aggressive your compaction strategy is. Let me break down what each one actually does in practical term. The minimum second is 3 millisecond. HBase wait until it has at least 3 files before compacting. If you lower this to 2, you get more frequent compaction but smaller I/O operation. If you raise it to 4 or 5, you'll get a fewer compaction but each one moves more data. The max setting is 10 prevents runaway compaction that could lock up your system. If you have 50 small file, HBase won't try to compact them all at once. It will take them in batches of 10. The ratio parameter is more complex. It's the algorithm that decide which files get selected for compaction based on their relative size. Don't worry, don't worry about the math. Just know the lower value means more aggressive compaction. The throughput bounds are for your safety valves. These prevent compaction from overwhelming your disk during the off-peak traffic periods. Workload specific tuning. This is where the magic happens, tuning for your actual user's pattern rather than theoretical benchmark. For real world like analytics dashboards or reporting system, you want to minimize the read performance. Even if you means more frequent compaction, users expect fast query more than accept fast writes. For fast write heavy workload like IoT data, ingestion or real-time logging, you need to balance the compaction overhead against write throughput. Too much compaction can create write bottlenecks. Here is a practical tip. If your application has predictable traffic patterns like heavy writes during the business hour or heavy read overnight, you can schedule these different compaction strategies for different time period. For time sensitive application where the constantly matters more peak performance, consider disabling auto major compaction entirely and running those during the planned maintenance window. Yes, these requires more operational overhead, but it eliminates the unpredictable factor. Uh, Region management best practices. Sorry. So, yeah, yeah. Optimal region sizing. Region sizing is one of those Goldilocks problem. Too small is bad, too large is bad, but just the right depends on your specific situation. Small regions create management overhead. Imagine trying to organize a library where every is in its own tiny section. You spend more time managing section than finding books. Okay. In HBase term, you have more metadata, more region server to coordinate, and higher chances of creating hotspots. Large regions have the opposite problem. When a region fails, recovery takes longer because there more data to replay. When you need to split a region, it's a bigger operation. Your load distribution becomes harder because you have fewer regions to distribute across the server. The 1 to 20 GB range works well for most use cases, but here's how to think about your specific need. If you have very hot data that get access constantly. Smaller regions let you distribute the load. If you have more archival data that get access infrequently, larger regions reduce the overhead. Monitor your current region sizes using the HBase shell. Just run list to see all table and describe table name to see the region details. Okay. Pre-splitting strategies. Okay, this is probably the single biggest mistake I see in HBase deployment. Every new table start with exactly one region, which means every write goes to the exactly one region server. It is like opening a store with only one checkout lane guaranteed bottleneck. Okay, the key the key to effective pre-splitting is understanding your row key distribution. If you're using time-based key, you need enough regions to handle your peak write rate. A good rule of thumb is to ensure no single region handle more than 1000 writes per second. For UUID style keys, hex string split works well because it distributes based on hexadecimal range. For sequential numeric key, uniform split gives you even distribution. Here's a real example. An IoT company was ingesting data from 100,000 sensors. They were using sensor ID as a row key, so they pre-split into 100 regions based on sensor IDs. This immediately distribute their write loads across their entire cluster instead of creating a single hotspot. Okay. The create command syntax might look complex, but it works mastering. You can also pre-split existing data, but it's much easier to do it at creation time. Region balancing. Okay. The balancer is your automated load distribution system, but it need proper configuration to work effectively. Think of it as an air traffic controller for your data. It need to know how much imbalance is acceptable before it start moving things around. The slop setting is critical. A setting of zero point 0.2 means one server can have 20% more region than average before the balancer kicks in. If you set this too low, the balancer run constantly, creating unnecessary region movement. If you set it too high, you will have persistent hotspot. Monitor the HBase web UI regularly. It shows you region distribution across the servers. Look for servers that are constantly overloaded or underutilized. These are signs that either your balancer settings are adjustment or you have a data distribution problem. Manual region move should be used sparingly. They are used for immediate hotspot relief. They can be interfere with the automatic balancer. Think of manual move as an emergency intervention, not regular maintenance. Okay. Hotspot prevention. Hotspot are the enemy of the distributed system, and they are especially problematic in HBase because they can't be easily fixed after the fact. Prevention is everything. The classic example is using current timestamp as a row key. Every write goes to the newest region, creating a hotspot that moves over time, but it is always there. It's like having a traffic jam that moves down the highway, still a traffic jam. Salting add a random hash prefix to distribute right, but be careful. It makes range scan more complex because related data is scattered. The trade-off might be worth it for the right heavy workload. Reverse timestamp work beautifully for the time series data when you typically query recent data instead of timestamp. You can use long dot max underscore value minus timestamp. This puts the newest data first and distributes the right over time. Composite key gives you the most flexibility. You can combine entity type, salted ID, and timestamp to create keys that distribute well but still support your query pattern. Always design your row key with distributed distribution in mind first. Then optimize the query pattern second. It's much easier to work around a complex query than fix hotspot. Okay. Memory tuning that works. Okay. HBase, let's start with HBase architecture. Okay. Think of HBase memory like a well-organized warehouse. You have three main area, each with a specific purpose, and optimizing them requires understanding how they works together. The block cache is your frequently accessed inventory that you keep close at hand. When someone asks for data, you check here first. It's not there. You go to the disk, which is much slower. The mem store is your staging area for the new inventory before it goes into the long-term storage. Everything you write goes here first, and when it fills up, it gets flushed to permanent storage on disk. The remaining heap handle all the logistic moving data around, processing requests, managing connection. This is when where the Java objects lives and where the garbage collection happens. The default 25% block cache and 40% mem store work for the many cases. By understanding these components let you optimize for your specific workload. A read heavy system might benefit from the larger block cache, and a write heavy system might need more mem store space. Okay. Heap size optimization. Okay, heap size is about balance between performance and stability. Too small and you will run out of memory. Too large and the garbage collection becomes the painful. Here's the key insight. HBase performance not just on depends not just on HBase memory but also on the OS level caching. The OS page cache automatically caches the frequently accessed file, providing another layer of performance optimization. If your allocation of the RAM to HBase, if you allocate all your RAM to the HBase, you will lose the benefit. The 50 to 70% rule leaves room for the OS to do the job. On 16 GB server, allocating 8 to 10 GB to HBase and leaving 6 to 8 GB for OS typically gives you a better overall performance. Warning signs are important to watch for. Okay, if you're seeing a garbage collection pauses over 100 milliseconds, your heap might be too large for the workload, or if you're seeing out of memory error, it might be too small. If you're seeing slow response time that correlate with GC activity, you have a tuning opportunity. Monitor your GC logs, they tell you everything you need to know about the memory pressure and collection efficiency. Okay. Block cache tuning. The block cache is your first line of defense against disk IO, and cache hit ratio is one of the most important metrics. You want this above 90% read heavy workload. The default 25% allocation work for balancing workload, but you can be much more aggressive for the read heavy application. I've seen systems performs well with 60% of the heap allocation to block cache, especially when combined off heap caching. Off-heap caching is a game changer for the large dataset. It let you have multi-gigabyte caching without garbage collection pressure. The trade-off is that off-heap access is slightly slower than on-heap, but it's still much faster than disk I/O. Okay, use the HBase web UI to monitor the cache statistics, look up for the cache hit ratio and cache eviction rates and cache utilization. If your hit ratio is low, consider increasing the cache size. If your eviction rate is high, you might need more cache or better access pattern. For write heavy application, you can reduce the block cache to 15 to 20% and allocate more space to mem store for better write throughput. Okay. Mem store configuration. Okay, the mem store is your write performance buffer, and tuning it requires understanding the trade-off between write throughput, memory uses, and recovery time. Large mem store mean fewer flushes to disk, which improves write throughput and create larger, more effective H file. But larger mem store also means longer recovery time if a region server fails, since unflushed data might be lost and need to be replayed for the write ahead logs. The global mem store size control the total memory allocation across all the regions on a region server. The lower limit triggers the flushing when memory pressure builds up. Uh, you want this to close the upper limit to avoid unnecessary flushes. The pre-region flush size determine when individual region flushes their mem store. Large flush size create the larger H file, which is generally better for read performance, but might impact the write latency during the flush operation. For high write throughput workload, consider increasing the global mem store size to 50 to 60% and large flush size for memory constrained environment reduced to 30 to 35% with smaller flush size. Monitor flush time in the region server logs. If flushes are taking too long, consider smaller flush size to reduce the impact on write latency. GC tuning best practices. Okay. The garbage collection tuning is often overlooked but can be dramatic impact on the HBase performance. G1GC is the recommended collector because it provides more predictable pause time. The 50 millisecond pause target the balance throughput with latency. Longer pauses can cause timeout and perceived performance problem. Shorter target might reduce the overall throughput. Steering uh, Detection can save significant memory in HBase due to repeated string like column qualifier, table name, and region name. This is essentially free memory saving. The advanced G1 option control how aggressive the collector is in the different phase. Don't change these unless you understand their amplification, but they can provide additional tuning opportunity for a specific workload. Monitor your GC log using tools like GC Viewer on in built-in JVM logging. Look for pause time, GC frequency, and memory allocation rate. If you are seeing frequent long pause, you might need to adjust the heap size or GC parameter. Here is a practical tip. Enable GC logging in production. The overhead is minimal and the insights are invaluable. When performance issue arise, okay, real world optimization win. Okay. Case study one, e-commerce platform. Okay. This case study demonstrated how understanding your workload characteristic can save massive infrastructure cost. The e-commerce company was experiencing the classic performance death spiral low query leading to more concurrent requests. Leading to even slower queries, they were ready to triple the cluster size, which would have cost $200,000 in additional hardwares and ongoing operational expenses. The root cause analysis revealed three key issues. First, their compaction ratio was too high, causing the excessive read amplification. Second, their product catalog table wasn't pre-splitting, creating hotspot on a popular product category. Third, the cache allocation was suboptimal for their read-heavy workload. The compaction ratio change from 1.2 to 0.8 meant smaller files stayed around and longer before compaction, reducing the number of files that need to be checked for each load. Directly address read amplification. Second, pre-splitting the product catalog based on the product category distribution that load across region, eliminating the hotspot during the peak shopping period. Increasing the block cache to 40% improved the performance for repeat query, which are common in e-commerce as user browse with similar product and category. The result was 60% reduction in read latency during the peak traffic period, completely eliminating the need for hardware expansion. The time investment was 2 days of the analysis and tuning. Case study 2, IoT data pipeline. IoT workloads are fascinating because they are predictable but challenging high write problem volume. Predictable pattern but strict requirement for the data freshness. This company has 50,000 sensors writing data every 30 seconds, creating a sustained write load that was overwhelming. The default configuration, the bottleneck wasn't hardware, it was configuration optimized for the read workload being used for the write workload. Okay. The key insight was the default memory allocation of 25% block cache and 40% mem store was backward for their use case. They didn't need much caching because they rarely read old data, but they need maximum write buffering. By increasing the mem store allocation to 50%, we reduce the flush frequency and improve the write batching. This allowed the system to handle burst write more efficiency and reduce IO pressure. The region pre-splitting based on the sensor ID ranges was crucial. Okay. Instead of all right hitting a single region, they were distributed across the cluster from day one. The salt prefix solution addressed the sequential nature of the sensor ID without salting. Sensor with similar ID would cluster in same region. The salt prefix distributed right evenly when still allowing efficiency range scan by sensor ID when needed. The 45% improvement in write throughput eliminating their ingestion delays and improved data freshness for downstream analytics. This is perfect example of tuning for your specific workload rather than generic best practices. Okay. Case study 3, financial analytics. Okay. Financial application present unique challenges because consistency and predictability are often more important than raw performance. A system that performs well on average but has unpredictable spike is worse than a system that performs consistently. Okay. The problem wasn't average performance, it was unpredictable spike from 100 millisecond to 5 second that were causing analytics problem to time out randomly. This inconsistency was creating business problem because financial reports have strict deadlines. Okay. The solution addressed three root causes. First, caches miss were causing unpredictable disk IO. Second, the row key design wasn't optimized for the time series financial query. Third, major compaction was running randomly and causing performance spike. Off-heap caching provide a larger, more stable caching without garbage collection pressure. This reduces the cache miss rates and makes performance more predictable. The row key redesign enable efficient range scan for time series data while maintaining even distribution. The account ID prefix provided natural partitioning when the reverse timestamp optimized for the real data query. Scheduled major compaction eliminated the random performance hit by running them during off-peak hours. We maintain the storage efficiency benefit without impacting the business operation. The result was 90% improvement in consistency. Maximum query time dropped from 5 second to 500 millisecond. This eliminated timeout and made the system predictable enough to meet the financial reporting SLA. Okay. Quick win checklist. Okay. This checklist is designed to help you implement these optimization systematically rather than trying to change everything at once. Okay. In the week first is all about understanding your current state. You can't optimize what you don't measure. So, establishing baseline metric first. Look at your region distribution are some servers headlines. Way more region, way more regions than others. Check your row key design for obvious hotspot pattern. Analyze your compaction patterns are major compaction running during business of hour. Okay. Week 2, focus on low risk, high impact changes. Compaction settings can usually be adjusted without downtime. The automatic balancer can be enabled and tuned safely. Memory allocation changes requires restart but are generally safe. Pre-splitting only affect new tables, so it's risk-free for existing data. Week 3 is more advanced optimization. Once you have seen the impact of initial changes, off-heap caching require more memory allocation but can provide significant benefit. Scheduled major compaction require operational process changes but improve predictability. The key principle is to change one thing at a time and measure the impact. Okay, this let you understand what's working and what's not, and it makes it easier to roll back if something goes wrong. Remember, optimization is an ongoing process, not one-time fix. As your data grows, users pattern evolve, and you will need to revisit these settings. Essential monitoring metrics. Okay, you cannot optimize what you don't measure, and you can't maintain optimization without ongoing monitoring. Focus on percentile metric rather than average. P99 latency tells you about your worst user experience, which is often what matters most of the business application. P50 tells you about typical performance. Don't rely on average. The average they hide the spike that causes the real problem. Throughput metrics help you understand the capacity and the growth trends. Monitor these over time to understand how your workload is evolving. Okay. And when you might need to scale. Resources metrics tells you about system health and help you identify the bottleneck. GC pauses time directly impacts on the user experience. Memory utilizations help you tune the allocation, and CPU uses pattern can reveal the hotspotting and inefficiency queries. Health metrics help you prevent problem before the impact users. Okay, compaction queue length can warn you about IO problem. Failed operation indicate configuration or hardware issue. Set up alerting on these metrics so you catch the performance degradation early. The HBase web UI provide many of these metrics out of the box, but consider deducting monitoring solution for the better visualization and alerting. A practical tip is create a dashboard that shows metrics and the multiple time range hourly, daily, and weekly. Views your understanding both immediate issue and long-term trends. Okay. Tools and resources. Okay. The right tool make optimization much easier and more reliable. Start with the built-in HBase tool. They are free and provide most of what you need. The HBase shell is invaluable for a quick diagnostic and administrative task. The web UI provide a real-time metrics and in particular uses during the optimization changes. Don't overlook the logs. They contain detailed information about what's happening under the hood. For production environment, I recommend using Excel data files for read all the metrics at one place. And JVM profiling tools are essential for complex performance issues. They help you understand memory allocation pattern, CPU hotspotting, garbage collection behavior, and GC viewer in particular uses for analyzing the garbage collection log. Don't forget optimization once you find the settings work. Script them consistency across the environment. This prevent configuration trips and makes it easier. Okay. Let me give you a quick demo for the Excel data pulse, how you can utilize for HBase monitoring solution. Okay. So here you go to the HBase, and if you click on the dashboard, you can monitor the number of regions and what is the file locality you are having, what are the store file size you are having, and what are the cluster requests you are getting, what type of requests you are getting, what is the hit ratio you are having in the cluster, and what are the table size minimum and maximum, and table request minimum and maximum. Okay. And similarly, you can see the region state, online, offline, and total, open, and any what are the states of the all available regions. Along with that, you can also see the table count distribution per host and region count distribution per host. And similarly, we can see the cluster JVM uses, request count, RPC count, region latency timeline, region loads, and all those metrics help you basically understand the overall problem in the system or calculate any of the performance issues that we are having. Okay. Now, if you go on the region servers, you can basically see things more through. Okay, so let's say if I click on one specific region server, I can monitor all those metrics. I can monitor the table hotspotting. I can monitor the JVM and GC, cache, region server operation, compaction metrics, and all of those details, which basically helps us understand what is happening in our HBase system. Similarly, you can create alerting for some of those metrics. For an example, if the number of in the GC count goes to some extent, you can create an alerting system via Pulse. Okay. And similarly, you can review all those metrics and you can basically review the individual table as well to understand what is happening inside what is happening inside the HBase system. Okay, if I go on a specific table and start reading the details of that, we can basically find all the minute details which we can use to basically understand the pattern and the long-term uses, and those metrics can be used to optimize our system much more better. Okay. Similarly, we can also monitor the service performance as well. Okay, like HBase master and the region servers can be monitored, and we can use them to tune the system further. Okay, that is it for the demo. Let me stop. Sorry, let me start sharing this screen again. That is it for the demo. If there is any Q&A, I'll be happy to answer any of the question.